Very glad to have everybody here today at Cal State Dominguez Hills. My name is Jared Head. I am a solar system ambassador from NASA's Jet Propulsion Laboratory up in Pasadena here in the Los Angeles area. I do not actually work for JPL. I kind of have to say that standard at the beginning of every presentation that we do. I am basically a representative who comes out and talks to folks on behalf of JPL, but I've been like vetted and approved and like knighted by JPL or something that I want to call it. Because as you can imagine, they get bombarded, they get a lot of speaker requests, and they can't fulfill them all, the people that actually work at JPL. So they had a great idea of having members in the public who know a lot about this industry, the aerospace industry, or exploration or planetary science, actually be able to volunteer their time to work at JPL. So that's what I do. I primarily work at Griffith Observatory. That's where I spend most of my time when I'm not working on my aerospace degree down in Fullerton. Really fun stuff. And today we're going to be talking to you about the exploration of Mars. So the exploration of Mars actually begins a very long time ago. When basically people were able to look up. You guys know what was the first thing we used to look at Mars? It wasn't a telescope. So our eyes, yeah. People just look up in the sky and happen to see this very bright red star in the sky, one that seemed to be a much deeper red than the other ones. And very interestingly, unlike all of the other stars in the sky, this star would move. And not only would it move in one direction, at one point it would stop and go the other direction as well. There's a lot of speculation from ancient peoples as to what Mars could be. It could be the god of war, it could be a multitude of other things. But once people really started to try to start studying Mars, some very interesting things happened. Indian astronomers in the 5th century were actually able to measure just about how big Mars looked in the sky, and they started trying to figure out exact distances, how far away Mars may actually be. And in their determinations, they were only about 10% off of what the actual size of Mars was. So, which is not bad for 5th century AD, I gotta say, pretty good for not having the kind of equipment that we have today. But for most of the time, Mars was sort of this red dot in the sky that we would watch, we would track, we would figure out where it is, and eventually we realized it was a planet. But it was sort of difficult as to whether Mars was going around the Earth or whether Mars was going around the sun. And then finally Copernicus was one of the first people not to necessarily figure out, but to get the church's permission to publish the idea of the Earth going around the sun and Mars subsequently going around the sun as well. Then a gentleman by the name of Galileo, who did not invent the telescope, but he was one of the first people that took telescopes, and instead of looking at the horizon for ships and other things, he decided to point it upwards at the sky. He was able to look at Mars and see that, yes, indeed, it was not a point of light, it was an actual, what we call a disk. So there was something there. So it wasn't just, a small place, it was a world in and of itself. And really, it starts to really come into play in the 19th century, when really good telescopes finally start to become the norm for astronomers. And during the early 1800s, in looking up at Mars, we were starting to begin to be able to map the surface of Mars, actually begin to see these features that we see on Mars. So on the left, we have images from Hubble, which are what we use nowadays to look at Mars. Over on the right are maps that are based off of some of the observations that were done in the early 1800s of Mars. One of the most famous astronomers that did this, Giovanni Schiaparelli, he noted that these areas sort of changed on Mars, and he called them canali. And then the people in the United States who were translating the book didn't really know Italian all that well, so they, instead of figuring out what canali actually meant in Italian, they just went with canals, as in irrigation canals, as in implying the idea that life may be on Mars and maybe it's farming right now or something, and we're watching the harvest go through as the year continues on Mars. Of course, that was incorrect. We now know nowadays that Mars is a pretty much lifeless, as we understand it, world at the moment. But the modern exploration of Mars began with this, which is Mariner 4. Now, Mariner 4 was the first spacecraft to successfully fly by Mars. Now, the Soviets had attempted to launch spacecraft to Mars all throughout the 1960s, but all 9 of them failed, either on launch, in orbit to get to Mars, on the way to Mars, or just as they arrived at Mars. So they were batting 0 for 9 in their exploration in the 60s. Yeah, sure. But we were able to get Mariner 4 there and actually see what Mars' surface looked like, because we had a pretty good idea as to what Mars' surface should look like. So we were expecting it to kind of be maybe like the Mojave Desert here in California. There were still some holdouts that said we should find cities and other things on the surface of Mars. But when we took that first photo of Mars with Mariner 4 close up, this is what we got. And this was up at JPL. And you'll notice that we're not using like a computer screen or anything to look at it. We're actually using like colored pencils and other things. We're actually coloring by number based on the data that they were getting back from Mariner 4 at that time. And when they finally colored everything in, this is what they were able to see on the surface of Mars. Now, this is not exactly the best way to go about things. We don't recommend that if you're going to explore space, you take photos and then color by number. This is just typically not a very great way of being able to figure out what you're looking at. So they did eventually get digital images back from Mariner 4, and this is what they were able to see. It just happened when they flew Mariner 4 past, there was a massive dust storm happening on the surface, so didn't really get to see the surface, so they had to wait until a later mission that actually went into orbit around Mars, one of the Mariner spacecraft, that then started taking surface photos of it. And then we sort of forgot about Mars for a little while, and then the Viking spacecraft came along, a twin mission with 2 orbiters and 2 landers, some of the most sophisticated spacecraft ever flown at that time, including of the crewed spacecraft that would fly humans. They landed on Mars in 1976. They did a multitude of research on the surface, including biological experiments to see if Mars may actually have life on it. They did the same types of experiments that we would do in a laboratory here to see if we could get bacteria to react and generate energy and waste, basically methane and other stuff. So as you know, we generate methane sometimes, so we look for that with the bacteria there as well. And those results were inconclusive. We still can either say yes or no based upon the data that we got back from those Viking experiments. One of them did, one of the experiments did not. So don't know on that. And then again, we forgot about Mars after Viking. It wasn't until the 90s that we decided to start returning to Mars with NASA's sort of faster, better, cheaper mindset of the 90s. And then we now have a very robust Mars exploration program. And now we know today, of course, that Mars is essentially the Mojave Desert, but about 200 degrees colder. So it is a very harsh place. It is not an easy place to have anything operate in. In fact, our success rate, including the most recent mission, InSight, landing successfully and operating on Mars, is 47%. So you are more likely to have your mission fail on the way to, en route, or in orbit, or landing on Mars than you are success. So it is very, very difficult. There's a multitude of reasons for that as well. And we'll kind of talk about those reasons as we go through our talk today so far. So this is all of the vehicles that we have landed on the surface of Mars. And very specifically, if you know a little bit about it, you'll know that the United States is the only country that has successfully landed vehicles on the surface of Mars intact, at least. The European Space Agency has landed 2 vehicles on Mars, although they did what we call very rapid lithobraking, which is basically they smacked into the surface of Mars and splatted across it at a couple hundred miles an hour. But we have quite a lot, and also another fun thing about all of these, every single one of these is not just from the United States that's made it to the surface, all of them are from JPL as well. So JPL is literally the only entity on this planet that has landed things on Mars. So in case you're wondering, why does JPL have such bragging rights? Well, they're the only ones who have done it. There's something, this is an elevation map of Mars, with the red areas being the higher areas and the blue areas being the lower areas. And what's some of the things that you notice about this elevation map? Anybody got any observations this morning of it? What do you see?
Blue crater.
Yeah, we've got a really big sort of depression down in the southern hemisphere of Mars. So, anybody notice anything else? So, do you guys know there's going to be a quiz? Just kidding about that. But the northern hemisphere of Mars is at a very low elevation. So we think at some point early on in Mars's history, something may have actually smacked into Mars and literally blew off the crust down to the mantle on the northern hemisphere. And then we can also notice that there's some areas, like sort of towards the middle of Mars right there, where it looks like water may have flowed into that area. So we're fairly confident that that northern hemisphere area was actually also an ocean as well, very large ocean on the surface of Mars. But there's something specific about all of these landers that we have right there. Do you guys notice what it is?
They're all on high
Pretty much the
elevations.
What's up?
They're all on high elevations.
I would go opposite that. It's,
Oh,
yeah, they're all in lower elevations compared to it. So, yeah, those blue areas are lower. You know, green and blue, that's below what we consider the average, sea level on Mars. And the reason that we want to do that is because Mars's atmosphere is very, very thin. It's only about 1% as thick as the Earth's atmosphere. So we want to have as much atmosphere as we can in order to slow down our vehicles when we're trying to land them on the surface of Mars. So we aim for places that are of low altitude because we can stay in atmosphere. Before we have to deploy our parachute, before we have to pull the heat shield off, before we have to separate, we can stay in those areas a little bit longer and slow down just that much, a little bit more, that can give us a little bit more of a chance for success of that vehicle to land there. Because landing on Mars is exceptionally difficult. There's just enough atmosphere that we have to do aerodynamic reentry. So we have to deal with heating, just like you would with the spacecraft coming through the Earth's atmosphere. But there's not enough atmosphere that you can deploy a parachute, like we do with spacecraft returning to the Earth, and you're A-OK on the parachute and can land safely. No, there's not enough. Our parachute will only get us down to about 350 miles an hour. And then we have to separate and come down under rockets, what we call retro propulsion. So very, very difficult sequence of things that has to occur very, very quickly. And we'll talk a little bit more about that later as we go on. Now, the surface conditions on Mars are not really in our favor either. As you can imagine, the surface of Mars, its average temperature is about minus 80 Fahrenheit, so very, very cold. In fact, if you'd like to, you can go to JPL's website. Under their Insight area, they actually do have a weather station on Insight, and they will give you the weather report for what the previous day was like on Mars. So right now it's fall on Mars, so Insight's getting average daytime temperatures of about minus 20 Fahrenheit, and then at night it's usually dipping down to about minus 120, minus 130 Fahrenheit at the surface. So we've got to have electronics that can handle that, and there's some parts where we've landed spacecraft on Mars where it'll dip down to minus 200, minus 250. And we've got to have a vehicle that can handle that. It's got to keep itself warm, all right? And deal with the radiation on Mars as well. Mars does not have a magnetic field like the Earth does. And Mars also does not have a thick atmosphere like the Earth does. Our magnetic field and our thick atmosphere here on the Earth takes care of most of the radiation that we would have to contend with. So basically the sun is not frying us all of the time, or instantly as soon as you step out. And also things like cosmic radiation and galactic cosmic radiation are not frying and zapping us as we walk out there either. Now on Mars, we don't have any of those protections that we have here on Earth. So we have to design systems that can handle those kinds of radiation hits and other things. And in addition to that, we have dust on Mars. I mean, if you've ever been out in the desert, there's lots of dust, right? I know some of us have a lot of dust in our house, maybe. But this dust is incredible. It is very fine dust. It's finer than some of the finest dust you can find here on Earth. It's almost like a powder at that point. And you can imagine most places on Mars that have this dust, if we were to land a vehicle there, it would not stay on the top. It would just sink through about 30 to 50 feet of dust. So that narrows down where we can land as well. In addition to that, we do not want to land somewhere where we blow up a huge amount of dust and then it all falls down on our solar panels of our vehicle, if it's using solar panels, because then we lose our ability to generate power and then our vehicle could potentially die at some point. And that dust also gets kicked up as well. It'll get lifted up by the atmosphere of Mars, and even though it's very thin, we can still have global dust storms on Mars. And those can last up to 8 months and block out all of the sunlight that we can possibly get. So overall, Mars, not a great place to send spacecraft to, especially to land them on the surface. Mars is not working in our favor in any sense in helping us out and trying to make anything happen. So what do we do when we're going to be landing something on Mars? Well, first we got to figure out where do we want to land it at. And in the case of InSight, which just landed the Monday after Thanksgiving last year, InSight is doing a very specific mission. It's doing seismology on the surface of Mars. So I'm sure many of us in the past 96 hours have refamiliarized ourselves with seismology, right? So yeah, just a little bit. So we're trying to study the interior of Mars using InSight, and we're using Mars quakes for that. Here on Earth, we can actually use the seismic waves from earthquakes and using seismometers detecting them, and we can actually figure out what the interior of the Earth is like that way. So we're using the same technique on Mars for that. And in addition to that, we're also trying to see what is the rate at which things impact Mars as well. So that way we can learn, what kind of protections are we going to have when we eventually send humans to the surface of Mars. Well, for most spacecraft when they land on Mars, they want to go to a really interesting place. So you want to do a lot of really cool science in this really neat place. But for InSight, you actually want to land it in a big, flat, boring area, because those types of areas are going to allow us to detect those Marsquake seismic waves much easier. So InSight is landing in the middle. InSight landed in the middle of a place called Elysium Planitia, which is basically a big flat area near the equator of Mars. Now, can you guys think of another reason why we would land near the equator of Mars as well? Anything?
It looks more level.
Yeah, to be a little more level, and that's a very good observation, because we need power for InSight, right? It's solar powered. And Mars is tilted, just like the Earth is. It's actually tilted a little more than the Earth, about 25 degrees on its axis. So if we land something towards the equator, overall, throughout one Martian year, which is just a little under 2 years to orbit around once, it will have access to more power than it would, say, if we landed at like a latitude where Los Angeles is at, or even further north. So we want to make sure our vehicle works as long as we can have it on the surface of Mars. So landing at the equator makes sure that the sun stays relatively overhead and provides the maximum power throughout a Martian year. So really important stuff with that. And as you can see here too, there's our landing ellipse again. Is it in high, low, or medium elevation?
Low.
Low, yeah, low elevation. So once again, we are aiming for that there. Now, we use a spacecraft that's in orbit around Mars right now called Mars Reconnaissance Orbiter. And Mars Reconnaissance Orbiter has a lot of instruments on board of it, but the most important instrument it has is a very large telescope that aims down towards the surface of Mars. And that telescope is about 12 inches across, and it's designed not to look at astronomy or other things like that. It's designed to look straight down at the surface of Mars. So what does that mean? Well, it can see a lot of things. So we are able to see fresh craters that have happened on Mars, where things have come in, impacted the surface of Mars, kicked away material, and we find ice underneath it. We find things like water ice, or carbon dioxide ice, carbon monoxide ice, other things there. One of my favorite ones is in the top right over there, where Mars Reconnaissance Orbiter happened to fly over a cliff, and while taking images, an avalanche occurred at that cliff, and it captured the avalanche mid drop right there. And then that one on the bottom is Mars Reconnaissance Orbiter. It flew just over the Curiosity rover when it was landing in 2012 and was able to snap a photo of it as it was descending under parachute through Mars's atmosphere. So, which amazing to be able to see these systems in action as that's actually happening on Mars. In fact, when Curiosity landed, we had it take photos. Jokingly, we called it the scene of the crime, where Curiosity landed at. You could see a multitude of things because we want to know what ended up happening to all of the components of the landing system. We want to see if our system worked and how we can model it better in the future so we can make better ones. So we can see areas like where some of the ballast, so some of the weights actually came off of our landing system and dropped it in. We can see where the back shell and the parachute landed at. And we've actually been able to take further photos of it and see that the parachute's flapping in the wind as well on Mars. We can actually see where the descent stage crashed at. We'll talk a little bit about that later today too with the landing system. And we can see where Curiosity landed itself as well. We can even see where the rockets that landed it blew away material from the surface to expose darker material below. So we have this incredible capability of being able to literally look at the surface of Mars and see things equivalent to if you were standing on Mars. We could actually take an image of you and note that that's the exact spot where you're at with Mars. Was that going to be your question?
Well, my question was, is this the actual color or is this just black and white?
No, this is in black and white. So a lot of the data that we get back is in black and white, and then we add color to it. And we have calibration targets to make sure that we're getting the colors right with everything. So most of the time when we're dealing with data, we do black and white simply because that's not only do we get really good data for black and white photos, color requires more data. It's a bigger file. And when we're talking to Mars, we're only really able to pull out at about 50 kilobits per second. So if you ever had a 56K dial-up modem for your internet in the 90s, we're a little slower than that talking to Mars. Which, I mean, it's a little amusing, but also we're talking over hundreds of millions of miles, so that's pretty good if you ask me, because sometimes my internet will run very slowly, and that's like, what, 15 feet? So, yeah. So, with that there. Now, when you build your spacecraft, you have to build it to very specific specifications. You want it to be able to handle the surface of Mars. So that means that we're going to be building your spacecraft inside of a clean room. But it's not just to make sure that the spacecraft is built correctly and that there's like no stray dust or anything that will ruin a circuit or something in it. We built our spacecraft inside of these clean rooms because we don't know, we truly don't know if there are places on Mars where there are still habitable conditions, or basically the areas where the conditions for life to exist are met. We do not want to inadvertently contaminate Mars with bacteria or anything that we have here on the Earth. So when you see folks working on Mars spacecraft and vehicles that go to the surface, you'll notice that they are fully stocked. They are fully covered in these suits that we jokingly call bunny suits with them there. So this was curiosity and testing at the spacecraft assembly facility at JPL, which, by the way, if you ever do get a tour of JPL, they take you up into the viewing room so you can look into this room while they're working. Also, just to let you know too, the Mars 2020 rover, which they're building right now in the spacecraft assembly facility, if you want to, you can actually go on YouTube, you can Google, you can search Mars 2020 Live, and they do have a camera that is looking down into the facility, and you can actually watch them at home if you'd like to, building the rover live with that. A couple of weeks ago, we watched them put the suspension and the wheels on of the new rover, and that was very interesting to see that in action. So we want to protect Mars and make sure that we're not inadvertently contaminating it. We don't want to accidentally bring stuff from Earth, and then a couple years from now, when we send that mission to maybe hunt for life, we find life, and then yes, we found life, we did it, and it's what we accidentally brought with us. So, whoops. Yeah, that would be slightly embarrassing, just a little bit with that. So again, once you've got your spacecraft built though, yes?
So they're all covered up,
Yes.
but the machine is not covered up. So how do you keep the contamination from the machine?
Yes, so that's a very good question. So first we build it in a clean room, and it is what's called a class 1000 clean room. So that means per cubic meter, so 1 meter cubed, there's about 1,000 particulate inside of that cubic meter. Just to give you an idea of like what you've got here right now, like in this room, it's about a couple billion particulate per cubic meter. So, so we really pull as much of the material out with filters and other things, and that air is recirculated, and it's recirculated in a certain fashion to allow easy flow, so that way the particulate will hopefully not stick to that. But they do clean it. They literally do like alcohol swabs all over every single piece that you could possibly think of with it. We will also put it inside of a heater and cook it at 400 degrees Fahrenheit for several days. So that takes care of it. When it's transported, it is put into a special clean container, and then that container is pumped full of nitrogen. All of the air inside of it is removed, and we replace that with nitrogen gas. Nitrogen gas is both inert, and also it will basically take care of any little microbes that may be surviving on the surface there. We even will keep it clean when it's being put in the rocket as well, and held in the rocket. And then the first time the vehicle, in this case, for like Curiosity would be exposed, the landing system will be exposed once the payload fairing of the rocket opens up. Which
Jared?
is,
I'm sorry, I
yes.
got a question when you're ready.
Oh yeah, so that'll open up at over 60 miles above the surface of the Earth. We're in space by that point, so that it's not running into anything. And then Curiosity is exposed for the first time when the heat shield pops off on Mars itself. Also, another nice thing is that when you're on your way to Mars, it takes about 6 to 9 months transit from Earth to Mars. So yeah, it's a bit of time. So you're spending that 6 to 9 months in the heat and cold of space, also the vacuum of space, also the radiation environment of space. So that 6 to 9 months also kind of works in our favor too, and making sure just about everything that could be alive is dead. Doesn't mean that there are microbes that can't survive that, because there are. There are some that can survive that, but we do everything we can to prevent that from happening. And
It may be a little bit off the subject, but if and when we do send astronauts on Mars, which I think will happen eventually.
It will happen, actually, yeah, for sure.
There is so much dust, like you were saying, on Mars. Would they have to have clean rooms on Mars, build clean rooms, because everything would get so contaminated? I just thought of that myself.
Yeah, absolutely. Yeah, one of the fun things about Mars dust is that it is highly electrostatic, so it will cling to things. Even if you try to push it off of your suit, it's going to cling to stuff. Lots of people are always like, well, why don't you just put windshield wipers on the solar panels for the Rovers, you smarty pants engineers. But the problem is that if we were to put those windshield wipers on there, we could wipe it off, but then the windshield wiper is going to get electrically charged from the static of the dust. And not only will that attract the dust to the windshield wiper, when we go the windshield wiper across again, now we're charging up the solar panel, and the dust will stick to the solar panel even more. So that's why we can't do those things. So yeah, we do have to worry about that. One of the ideas that the at least human spaceflight division of NASA is working on is this idea of suit ports. So instead of having an airlock that you go into, you would have like this little area where you plug in the back of your suit. You clean off the back of the suit somehow, and then the back of the suit opens up inside, and you kind of like step out of it that way. And then you step back in if you want to go outside, and then close the back, and it closes behind you, and you step out like that. So that way you keep the spacesuits outside of the vehicle without tracking dust in. Because the surface of Mars is also not particularly good to like breathe in as well. It's got lots of chemicals like perchlorates and other stuff that basically wrecks your thyroid and other organs with you. So not particularly a good thing to do, as if the radiation was bad enough with that there. So yeah. So once you've got all your stuff ready to go, it's time to go to Mars. You guys ready to send your stuff to Mars? All right, what are we sending to Mars? Are we sending your car to Mars? Real quick for you there? No? Are we? Oh, okay. All right, so after we fully built everything, remember, we have to keep those cleanliness specifications going. So with InSight, as it's being transported, we have to keep it extra clean, extra safe from that. We launched it from Vandenberg Air Force Base here in California. This is the first vehicle that launched on an interplanetary flight from here. Most of them were done in Kennedy Space Center, but they moved InSight to here in California because InSight is very, very light. It was under 1,500 pounds to send all of that there. That's very well within what we can do with our rockets. And in addition to that, it's become very busy at the Kennedy Space Center. If you've been paying attention to spaceflight over the past decade, you'll notice that all of a sudden there's lots of players in the game, and they all want to launch their rockets. So it was moved to Vandenberg to kind of free up some of the schedule with that there. So at Vandenberg, you still have to put it all together inside of a clean room. So you just can't decide to open up the door at some point and wheel this in and then close the door and clean it up a little bit. No, you have to keep it clean throughout the entire process. And that just goes to show you how big InSight actually is. So we had to take this lander, which is about this big, and fold it up into this system to land it on the surface of Mars. So kind of had to origami it in there. And then there's our payload fairing in order to get it in our rocket to protect it during the early part of that launch. And then you go and you put it on a really big rocket. So in this case, InSight launched on an Atlas V rocket. If you ever watch a rocket on TV, You probably don't really think about how big they are, but they are quite big. The Atlas V is about 190 feet tall, so it's pretty big. We're pretty close to SpaceX here. If you ever want to wander on down towards their headquarters where they build all this stuff at in Hawthorne, they have one of their boosters that actually did fly and land sitting out front. You can walk right up to the street corner where it's at and take a look at it. And that's the first stage. The second stage isn't on top of it. And the first stage itself is 150 feet tall. If you put the second stage on it, then it's 220 feet tall. So rockets are really big machines. Yes?
Is that located at Crenshaw and 120th
Yes.
Street?
Yes. Yeah, right in that area, right by the 105, right at the airport.
Yeah.
In there. So yeah, so you just walk right up and take a look at it. So yes.
I don't know much about this stuff, so is the curiosity about Mars
Mhm.
just in general, or because there's ice there? or
Yeah,
something?
well, I'll talk about the missions specifically as we're coming up to it in just a bit. But yeah, we're still getting to Mars at this point. So once we get to Mars, then we'll talk about what we do on Mars with that. So yeah, it really but we do think about these things before we send them to Mars. But yeah, we'll talk. Every robot does something very specific to itself, and we'll talk about that just a little bit. So with this rocket, we launched it from Vandenberg on May 5th, 2018. It was very foggy up in Vandenberg, as it often is. But, like that engine, and let it go, and you are on your way to Mars.
Wow.
So, and they had some very good forethought to put a camera above the fog, so you get beautiful images like this one that's coming up that I absolutely love right here.
Yeah. Oh my goodness.
This rocket, coming out of the fog
That's
right there. Yeah, beautiful, right? So
Yeah.
Yeah.
now this is putting out about 1 million pounds of thrust, which is somewhere on the order of roughly about 70 million horsepower in order to get it off of this planet. And it's a 2-stage rocket. So once our first stage runs out of fuel, we turn it off. This rocket is not reusable, so the first stage just falls back into the ocean. But we separate, and then once you're ready to go, the second stage ignites, and you will officially be making your way to Mars. And then we'll see it ignite here, and there we go, we're lit. And then eventually, your second stage will shut down its engine, and you're on your way to Mars, there we go. And then you gotta separate from your upper stage, as InSight did, and there you go, on your way to Mars. Piece of cake, right? It is rocket science. To make that happen. Now, this is really where math starts to happen, as if it didn't happen before this, which is that when you launch for Mars, you don't really actually aim for Mars itself. So when we launched InSight, we weren't aiming for Mars here at the launch. We were aiming for where Mars would be at its arrival, which is almost a third of the way across our inner solar system. And we have to do that because of this thing right here, the sun. The sun complicates things. Its gravity makes you go in a curve instead of a relative straight line on its way to your object. And in addition to that, we don't really want to launch just whenever we feel like it, because we want to make sure our spacecraft spends as little time in space. Space is a place where some things can go wrong with our spacecraft, right? So we want to make it as quick as possible. So we have launch windows. These are periods of time where we have just enough rocket power that we can actually launch something to the surface of Mars. These windows only last about 30 days, and they happen every 26 months. So if you do not launch your spacecraft in that 30-day window, you're going to get to wait just a little over 2 years for your next launch window. That's also for coming back from Mars as well. So when we start sending people to Mars, we need to make sure those systems are basically going to work perfectly. Because if not, you could end up stranding people on the surface of Mars for another 2 years. I'm sure you guys saw The Martian, right?
Yes.
Yeah, and physics played a really important role in that, right? Because Mark Watney couldn't just come home whenever he wanted to. They had to wait for the launch window and have him come back at just the right time for that. So yeah, InSight was supposed to launch in March of 2016, but there was a problem with one of its instruments. They couldn't get their seismometer to basically take in the data as well as they wanted it to. And they couldn't get it done in time for the launch window. So guess what they had to do? Wait 26 months. So, yep, and storing the spacecraft for 26 months at a cleanliness so that it can go to Mars is not cheap. So, but it was a very important mission, so we decided to go ahead and allow that to occur. But as InSight's on its way, you can see that sometimes it will fire engines that allow it to guide itself a little more precisely towards Mars. And actually, the rocket that we used, that Atlas V, was so precise. Our first 2 burns that we were planning to do, we didn't need to do them. So it launched it right where it was supposed to be at, within about 5 seconds of the expected time for the spacecraft to travel through that point in space. That's pretty good. So we were able to save that fuel and further refine when we got even closer to Mars to do even more burns of those small engines to line it up. And then eventually we've got to land on Mars, right? So once we are on our way to Mars, we've got to land it there, right? And that's pretty important. And like we said, that's pretty difficult too, right? So, because of those multiple things that we have to worry about with it. So in the case of InSight, on that Monday after Thanksgiving, we first had to get rid of the system on the back that was powering it on the way to the surface. And then we've got to enter the atmosphere of Mars, which we're doing at about 13,000 miles per hour. So pretty quick. And parts of that heat shield are going to heat up to about 5,000 degrees Fahrenheit. And there's about 3/4 of an inch of it. So that's separating it from 5,000 degrees Fahrenheit. And then when we're moving at Mach 2, we're going to deploy our parachute. These parachutes are designed to open up at supersonic speeds. And then we'll get rid of our heat shield. And our landing radar will figure out where the altitude is and what the speed is. And then we'll literally just drop InSight. And then once it gets to the right point, they'll fire rocket engines. And those rocket engines will fire at full thrust until it's just above the surface and then stop. And that's it. That's how it works. So, yep. And it worked. And then we were able to deploy. And then we wait about a half hour to make sure as much dust as possible settles. And then we deploy the solar panels at that point. Yes?
And you said it withstands 5,000 degrees.
Mhm.
What kind of material is that?
Yeah, carbon ceramics is what allows us to do that. So, which is that when you launch for Mars, you don't really actually aim for Mars itself. So when we launched InSight, we weren't aiming for Mars here at the launch. We were aiming for where Mars would be at its arrival, which is almost 1/3 of the way across our inner solar system. And we have to do that because of this thing right here, the sun. The sun complicates things. Its gravity makes you go in a curve instead of a relative straight line on its way to your object. And in addition to that, we don't really want to launch just whenever we feel like it, because we want to make sure our spacecraft spends as little time in space. Space is a place where some things can go wrong with our spacecraft, right? So we want to make it as quick as possible. So we have launch windows. These are periods of time where we have just enough rocket power that we can actually launch something to the surface of Mars. These windows only last about 30 days, and they happen every 26 months. So if you do not launch your spacecraft in that 30-day window, you're going to get to wait just a little over 2 years for your next launch window. That's also for coming back from Mars as well. So when we start sending people to Mars, we need to make sure those systems are basically going to work perfectly. Because if not, you could end up stranding people on the surface of Mars for another 2 years. I'm sure you guys saw The Martian, right?
Yes.
Yeah, and physics played a really important role in that, right? Because Mark Watney couldn't just come home whenever he wanted to. They had to wait for the launch window and have him come back at just the right time for that. So yeah, InSight was supposed to launch in March of 2016, but there was a problem with one of its instruments. They couldn't get their seismometer to basically take in the data as well as they wanted it to. And they couldn't get it done in time for the launch window. So guess what they had to do? Wait 26 months. So, yep. And storing the spacecraft for 26 months at a cleanliness so that it can go to Mars is not cheap. So, but it was a very important mission, so we decided to go ahead and allow that to occur. But as InSight's on its way, you can see that sometimes it will fire engines that allow it to guide itself a little more precisely towards Mars. And actually, the rocket that we used, that Atlas V, was so precise. Our first 2 burns that we were planning to do, we didn't need to do them. So it launched it right where it was supposed to be at, within about 5 seconds of the expected time for the spacecraft to travel through that point in space. That's pretty good. So we were able to save that fuel and further refine when we got even closer to Mars to do even more burns of those small engines to line it up. And then eventually we've got to land on Mars, right? So once we are on our way to Mars, we've got to land it there, right? And that's pretty important. And like we said, that's pretty difficult too, right? So, because of those multiple things that we have to worry about with it. So in the case of InSight, on that Monday after Thanksgiving, we first had to get rid of the system on the back that was powering it on the way to the surface. And then we've got to enter the atmosphere of Mars, which we're doing at about 13,000 miles per hour. So pretty quick. And parts of that heat shield are going to heat up to about 5,000 degrees Fahrenheit. And there's about 3/4 of an inch of it. So that's separating it from 5,000 degrees Fahrenheit. And then when we're moving at Mach 2, we're going to deploy our parachute. These parachutes are designed to open up at supersonic speeds. And then we'll get rid of our heat shield, and our landing radar will figure out where the altitude is and what the speed is, and then we'll literally just drop InSight, and then once it gets to the right point, they'll fire rocket engines, and those rocket engines will fire at full thrust until it's just above the surface, and then stop. And that's it. That's how it works. So, yep, and it worked. And then we were able to deploy, and then we wait about a half hour to make sure as much dust as possible settles, and then we deploy the solar panels at that point. Yes?
And you said it withstands 5,000 degrees.
Mhm.
What kind of material is that?
Yeah, carbon ceramics is what allows us to do that. So, yeah, and that is a one and done with that kind of material as well. So, because it's even hotter than the space shuttle had to contend with on re-entry with it itself. So, yeah. And that heat shield is also what we call ablative. That means that the material literally vaporizes away as it pulls the heat away from the surface. So basically the heat shield loses about 1/3 of its mass in vaporizing away. So yeah, it's a little scary if you think about it with what it's like. But how do we test all this stuff? Because we can't just like go to Mars and test all this stuff, right? Because that's expensive. You don't want to like, all right, we're going to test a parachute this mission, and then we'll wait 2 years, and we'll test the heat shield this next mission, and we'll wait 2 years. So that we go all around the Earth, and we try to simulate what the conditions are going to be like. So this is this is the world's largest wind tunnel up at NASA Ames in the Bay Area, up in Silicon Valley near San Francisco. And they're getting ready to do an engineering test for one of Curiosity's parachutes to make sure that the system is actually going to be working like they're expecting it to. Because the last thing you want to do is have your robot splat on the surface of Mars. Because there have been missions where that's happened. So let's see how the parachute does. Looks good. Looks pretty good. Yeah, not bad. And we have to remember too that this parachute's about 60 feet across. This is not a small parachute. And this parachute also has the handle opening up at twice the speed of sound. That means that those shock waves that generate sonic booms, the parachute has to be able to take that being generated on the inside of it as it opens up. That's really, really tough to make a parachute that can do that.
Wow.
So, yeah, it's very, very hard. Yes?
On looking at some of the video on Apollo's reentry, they had 3 parachutes.
Yes.
Is the reason for just one is the size?
Yeah, so we have to take weight considerations into our decisions as to what we're going to do for that. And on Mars, parachutes don't really net us much slowing down. So 3 parachutes weighs more because you have 3 parachutes instead of 1. 3 parachutes also generates more drag force, which means that you have to have a stronger system attaching those parachutes to your landing system, which means that that's probably going to be heavier as well. In addition to that, 3 parachutes means there are 3 places where you can have a failure occur at. So there's more chances for failure with that. So if you lose 1 parachute, then you might end up not being able to have those 2 work correctly. And also those 3 parachutes, when they deploy, they could interact with each other as well. And that would end up maybe causing none of them to open up, and then our vehicle smacks into the surface at way too high of a speed to survive. So it is a compromise to just do 1, but it's essentially physics making us have to compromise that. There's just no way we can really get around that. So, yes?
And I apologize for
Oh, no. But questions are A-okay, by the way, if you have questions, so yeah.
Now, what is the gravity element to Mars, or is there gravity?
Yeah, so there is gravity on Mars. We do have a little bit. That's one of the things that's sort of in our favor for design work, which is that Mars's gravity is 1/3 of what we have here on Earth. So take your weight, divide it by 3. That's what you weigh on Mars. So pretty nice, right? And a lot of people want to go to Mars at that point. Mars is smaller than the Earth, but Mars actually has the same amount of surface area as the Earth does that you can explore here on the land. Because Earth is mostly what?
3/4 water.
Yeah, mostly ocean. So we have the same amount of land area here on Earth as we have on Mars. Simply because even though Mars is smaller, there's no ocean there. So yeah, so if you can imagine, we've got literally all of the land on Earth to explore on another planet. So we've got a few areas to go to. Yes?
How much of the surface of Mars is free of dust?
Roughly, so of the landable areas on the surface of Mars, it's about 9%. So we are still very limited even on what we can do at the moment. So yes.
So, you're already preparing the next rover.
Yes.
What happens to this one?
It will still operate. We'll keep it running until it dies, basically.
And you just leave it there?
Yeah. Yeah, we won't bring it back,
Okay.
unfortunately. Yeah. Yeah, we always like to think of these as sort of like our robotic emissaries to the stars. Once they stop moving, they're a monument to humanity, I suppose. So, at that point.
Jared, also, I wanted to ask about things coming back.
Uh-huh.
I read or saw in a movie or something that once we send the astronauts there, they're there for forever because they can't come back. There's no way-
Potentially. I know NASA at least is still looking at bringing astronauts back. We'd like to have crew rotation ability, but there are people like SpaceX that are saying that you're going there and you get to stay there.
That's
So,
good.
because it does cost just as much to bring you back from Mars as it does to get you to Mars. And it's also just as dangerous to get back from Mars as it is to get you to Mars as well. So you're almost safer staying on Mars than trying to come back to the Earth. And also, we kind of look at it as when we started to cross the Atlantic in the 17th century. You know, when they crossed the Atlantic, those people did not have the intention of returning when they came over to North America. So it's kind of what we're looking at. Our new sea is a silent one. So it's not the Atlantic; it's the vacuum of space between us and the other planets. So we'll have to see how that goes. So yes.
Thus far, through the explorations, has there been any value-added materials or substances found so far?
Oh, like things we could use on Mars.
Materials, like ore or something like that.
Well, we find that there's a lot of iron oxide on Mars and other things like that. But most of what's on Mars, it would cost significantly more to bring it back to Earth than it would be worth. So for now, mining Mars is probably not going to be happening anytime soon. Or at least, let me correct myself on that. Mining Mars for using stuff here on Earth is probably not going to be happening anytime soon. But I will fully answer your question just a little later in this talk here. So you guys are thinking ahead.
I have a
so really
question.
like this. So yeah.
In order for the parachute to work, obviously there has to be some amount of atmosphere
Uh-huh.
rather than a vacuum.
Yes. So we do wait until it's in the atmosphere for that. So yeah, usually at about 50,000 feet above the surface of Mars is where we deploy that parachute. So not as much atmosphere as near the surface, but there's still enough atmosphere to open the parachute up. So you would probably imagine that a wind tunnel here at sea level's probably gonna not be what it's like on Mars, right? Yeah, well, I mean, we thought about that. So we actually put our system on top of a test that was already happening anyhow. They launched a weather balloon from Hawaii, and this weather balloon took a basically small rocket up to about 120,000 feet, and then we released that small rocket. We spun it up to stabilize it. That way we didn't need a computer to stabilize it. We fire that engine, and we get it up to the speed of entry, so at about Mach 2. And we get it up to about 300,000 feet, which at 300,000 feet above the surface of the Earth, our atmosphere is about as thin as Mars is. So we're gonna stop our spin, we'll pop off our filter on our camera to make sure that we get really good footage. And this test was actually to test a new type of heat shield system, which inflates. So instead of having a solid heat shield, You have a heat shield that these sort of like gas canisters that would fire your airbag in your car heats up, so that way we can reduce the weight of our heat shield. So, and it worked perfectly. So now, after this, it was time for our little parachute on board to give it a shot. So we used a balloon, which is a system that generates drag to pull the parachute out to help add a little extra weight on there. Let's see how our parachute does. Ooh, that's not good. So, yeah, if that were to happen with your vehicle entering on Mars, that's it, game over. You're going to continue to the surface and you'll impact the surface at just below supersonic speeds. You see the parachute rips even before it opens, and then it just absolutely shreds once it fully opens. So, not good, right? Back to the drawing board. And that's really what engineering and science is, right? If you're not at the drawing board, you're not really actually doing a lot of work. So honestly, so we went back and redid it, and we were like, okay, so we put it on a sounding rocket. These are small rockets that we can launch very high up into the Earth's atmosphere. And okay, let's give it a try again. Let's make sure that we can get this right with our parachute. So this one launched it again, up to about 300,000 feet. And then we deploy the back end of our rocket, and now we are ready to have our parachute deploy. So let's see how this test of the parachute for the 2020 Rover went. And perfect.
It's a good one.
So, yep, good open. Let's watch the high-speed footage as well. This is just really beautiful to see this in action here.
Oh, I bet.
Yeah, take a look at that. And then the hard part, which is those little lines snapping at supersonic speed. Perfect. Handled it excellently. So just what we want to see. And when all of this works together correctly, you end up getting your vehicle on the surface of Mars. And once you're on the surface of Mars, as someone was asking earlier, now it's time to have some fun. So, obviously we don't send people to Mars, especially people not in spacesuits. But this is at the Mars yard up in JPL. We can actually recreate wherever your rover is on Mars, in the Mars yard, and we can figure out how to drive it. Because yes, the actual people who drive the Mars rovers, they will go out with these full-scale mock-ups that weigh the same amount as they do on Mars and basically drive them over things and see how it does. Now these are our series of rovers that we've sent. We've got 3 generations of rovers right here. We've got Sojourner down here, which is a part of the Mars Pathfinder mission that landed in 1997. We have the Mars Exploration Rovers, which was a twin rover mission that landed in 2004. And then we have Curiosity over here, which is part of the Mars Science Laboratory mission. And you can see that they get bigger and bigger and bigger as they go in, because we got much better at landing heavy things on the surface of Mars. The problem with Mars is it's not so much can we chuck it at Mars. We're pretty good at throwing stuff at Mars. The hard part is landing that heavy stuff on the surface of Mars. And right now, with our system's Curiosity in Mars 2020 is right at about the limit of what we can land on Mars, roughly about just under a ton of weight with it. But Sojourner was in 1997. There had not been a wheeled vehicle sent to anywhere off of the Earth since the Lunokhod rovers that the Soviets launched to the moon in the 70s. So we wanted to see if it would actually work in principle on Mars, and it did. And Sojourner was designed to last for 10 days. It ended up lasting for 3 months on the surface of Mars. It had 2 instruments. It had a camera on board, and it had a spectrometer. So it would basically put this instrument against the rocket. It could say this rock is made out of silicate and carbon and a few other elements and other things, and here's how much of that element is there. So when we were looking at Mars with our spacecraft that were in orbit, we saw that there was a lot of evidence that said that water was once on the surface of Mars. So the Mars Exploration Rovers were sent as a mission to basically investigate whether water had ever been present on the surface of Mars. So we sent 2, Spirit and Opportunity. They landed in January of 2004. They were designed to last for 90 days, so 3 months. Spirit ended up lasting for 6.5 years on the surface of Mars before it conked out. And then unfortunately, just earlier this year, we announced the end of mission for Opportunity because a very large dust storm happened on Mars. Spirit and Opportunity were solar powered. And unfortunately, Opportunity just could not get the light through the dust. And then after that, the dust likely has completely covered Opportunity as well. So Opportunity lasted just a little under 15 years on the surface of Mars. Remember, 3 months. That's all we were supposed to get out of it. 3 months, maybe like 600 to 800 feet of driving out of it. Opportunity lasted 15 years, and it drove 27 miles on the surface of Mars. So it holds the record. So it drove even further than the lunar rover vehicles the Apollo astronauts used on the surface of Mars. So, which is amazing for us. And the more amazing thing is that where Spirit landed, it was a very volcanic plane. We were hoping it was going to land in the middle of what we thought was an inflow where water came in, but actually it landed in the middle of a basaltic rock lava field. So Spirit had a very hard time with all of its exploration. We called it the little rover that could. It basically had to fight for everything it got. And Spirit also broke down very quickly too because of the rough terrain. But Spirit fought through and found evidence that there actually had been hot springs on the surface of Mars. And if you know anything about hot springs, you know that they're a pretty good place for life to exist with that there. Now, Opportunity sort of had a lot of stuff handed to it. When Opportunity landed on the surface of Mars, we used that airbag system to allow it to bounce across the surface, and the airbag literally rolled right into the middle of a crater. So we did like a nice hole-in-one from Earth. It was only like what, 330 million miles hole-in-one, so no big deal. The interesting thing about this crater is that it landed right in the middle of it, and you see those rocks up at the top right there? That's bedrock, right in the side of that crater. And if you know anything about geology, bedrock is truth. It's the truth, nothing but the truth, the whole truth. That's it, right there. That will tell you exactly what was going on at this time when those rocks were around. And it went up to those rocks, and it found this.
Oh my goodness.
Yeah, blueberries. Somebody left a bunch of blueberry snacks in it. No, I'm just kidding. But they are called blueberries, but they are a specific type of mineral called hematite. And hematite is iron oxide, and these blueberries form when that iron oxide is taken through like a river and rolled down the surface of that river for a very long distance. So that was basically, guess what? Straight evidence, actual evidence that you cannot refute this evidence that water was once there on the surface of Mars. And long term too. So that was pretty important with it. And this is one of the last images of Opportunity that we were able to get back. You can see that in February of 2018 here, it already had a lot of dust on its solar panels. And then that storm that started up in June of 2018, that basically did it in. So covered up its solar panels too much. It lost power. We were able to get one final image from it, which was basically a bunch of static. But that was it. End of mission. And now we will review the data from Opportunity and likely still be making discoveries from its data for at least the next 5 to 10 years to come. So, yes?
So this was powered totally by solar power?
Yeah, solar power. Yeah, the solar panels. Very interestingly, they make about 1,500 watts of power to drive around with and roll their little instruments with and other things like that. But the dust would eventually fall on them, and then sometimes during the mission, they'd be graphing out the solar power and it's starting to go down, and then all of a sudden one day, it would go up like 400 to 500 watts and then stay there. So what would end up happening is that these dust devils on Mars, every once in a while, dust devil would go over one of the rovers and it would blow the dust off of the solar panels. So we got really lucky a lot of times with these rovers, where the wind on Mars would just so happen to blow the dust off. And we were hoping that that's what would happen with Opportunity, and that Opportunity would then ping us back and go, hey, I'm alive. What do you want me to do? But unfortunately, sometimes when you've rolled the dice a lot, sometimes it just stops your luck. So, yes?
What was the probability of Mars being impacted by meteors, obstacles from other places that would impact?
Oh, like hitting Mars itself?
Right.
So what's
like on the moon, you have all these craters.
Oh yeah. Well, on Mars, what's the probability of things hitting Mars? Absolutely, it's 100%, 1-to-1. So there's stuff that'll hit Mars every day.
So those things that are found on Mars don't necessarily have to be natural items.
Yeah, actually, we have these rovers and Curiosity have actually found meteorites on Mars. So things that are not from the surface of Mars and that are very similar to the meteorites we find here on Earth. But one of the things is that we find a lot of the same minerals at these landing sites all over the place on Mars when we know what to look for. So yeah, with the Opportunity rover, Spirit ended up finding hematite as well. Spirit also found gypsum, which is a mineral that forms in water here on Earth as well. And then we'll talk a little bit in just a few slides about Curiosity finding evidence for that as well in its landing site, and they're on the other side of the planet. So if it's planet-wide, then it's rather conclusive for that. Yeah.
Just a quick question.
Yeah.
In the movie The Martian, in the beginning of the movie, they ran into a storm.
Mhm.
And I think they said the storm was made of silica.
Yes, dust.
So,
Yeah.
oh, okay, so,
Yeah. Another word for like sand or dust is silica and particulates.
oh, I
So,
see, okay.
Yeah, so it's the same thing.
Professing my ignorance.
And that's actually a really good thing to bring up about the dust storm at the start of The Martian. That was probably the most inaccurate part of The Martian.
Yeah, I was just wondering, was that accurate?
Yeah, it would not be that bad. It wouldn't be tipping your on the verge of tipping your spacecraft over. A 100-mile-an-hour wind on Mars would hit you with about 1 mile an hour of force.
Wow.
So yeah, piece of cake with that. All right, all the hands are coming up now. Yeah.
Do you know if they have ever considered putting a blower on those to blow off the,
They actually.
like the computer does things?
Yeah, they actually have. One of the problems is that for you to have that, you have to have pressurized air in order to do that. And for pressurized air, you have to put it in a pressure system, and you have to build those so that it can handle the pressure that you're putting in it. And we have to remember that the atmosphere of Mars is very low pressure, so we're going to have to pump a lot of air in it, which means we're going to have to get it at very high pressure, which means it's going to be a very heavy system. So yes, it's all about weight. So yeah, in space, as we say, in spaceflight, every ounce counts. So yeah, it really does. So yeah, but yeah, we've thought about that. We've thought about light systems. We've thought about dropping water on them and other things. It just ends up becoming too complicated. There's too many things that can go wrong, or it's too heavy, or it ends up being too expensive within the budget of the vehicle. So.
It's over. So is the chatter.
All right. So our Mars exploration rovers were solar powered, which, as we learned, was not particularly advantageous on the surface, especially if you want to take a laboratory to the surface. You need a lot of power to operate those instruments. So we sent Curiosity in 2011 and landed in 2012. And Curiosity is not solar powered. It has this very big white thing on the back right there with those fins right there. That's called an RTG, a radioisotope thermoelectric generator. So what does that do? Well, we have got plutonium in there, and we are using the heat of the plutonium decaying to generate electricity. So it's nuclear power. So that means that if there's a dust storm, we can still operate during it. At nighttime, we can operate. In the terrible conditions, we can operate the rover, and it does. And when that dust storm was happening last year, it just continued chugging along right in the middle of it. And in fact, we were able to get some of the first measurements of what was happening in the dust storm at the surface, simply because it could operate during that dust storm. Yes?
Oh, in the nuclear, are you just depending on the natural decay rate?
Yep. So it will eventually run out of juice.
But it's a natural decay, you're not augmenting it or controlling it?
No, yeah, we're not running a reactor or anything on board. It's just, we just put a bunch of plutonium in a little can.
Natural rate of,
Yep, yeah, we're not, we didn't fly a nuclear reactor on board of it. So we're not at that point yet with it. But yeah, just using the natural decay from it, yeah. And Curiosity is about the size of a car, so it's a very large vehicle, the largest thing we've landed on the surface of Mars, and it has a tremendous amount of instrumentation on board as well. This is its turret at the end of its arm. We have a microscope on it. We have a system to drill into the surface and measure things. A whole bunch of cameras and other instruments as well to measure that. And we'll spin the turret and put it down, spin the turret, put it down, spin the turret, put it down, and kind of go through all of them when we're looking at a rock or something. But it's pop quiz time. I told you guys there was a quiz, right? So one of these photos is from Earth. One of these photos was taken by Curiosity on Mars. So which one do you think is Mars? Which one do you think is Earth?
Left.
The one on the right side.
So if you think, so raise your hand if you think the one on the left is Earth. Raise your hand if you think the one on the left is Earth. Raise your hand if you think the one on the right is Earth. Raise your hand if you think the one on the right is Earth. All right, here we go. Let's see who is right.
Yeah.
There you go.
You get to keep it on.
That is the same type of rock, though. That is a conglomerate rock. That forms at the bottoms of things like rivers, and rivers that have been there for very long periods of time. So yeah, it does look like a hunk of concrete, indeed. Yeah, and so Curiosity, when we found these rocks, we got really excited. And we went up and we analyzed the rocks, and we found stuff that life needs. One of those is schnapps. So, which, yeah, I know, sometimes more days than others, but schnapps is carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So those are the 6 elements that all life needs. I use these 6 elements. You all have these 6 elements. Your pets, your lawn, trees, blue whales, the thing growing in the back of your refrigerator you should throw out. We all share those 6 elements here on Earth. We also found that the water that was flowing there was fresh water. So you and I could drink it. And liquid water is needed in life because liquid water is able to move things throughout your body. It can move nutrients and help remove waste. That's why it has to be liquid, not ice, not solid water or gaseous water. It's got to be liquid water. And that fresh water makes it more likely that you can actually use it. And there's a source of energy on Mars, the sun, right? Because you know that we all basically run on sunlight here on Earth, right? Like I had cereal this morning for breakfast, so I got my milk from a cow, which the cow got its energy from the grass, which the grass got its energy from the sun. So, or if you eat a salad, you're getting your energy from the sun. So technically, we all run on sunlight here on the Earth, right? So, yeah. So billions of years ago on the surface of Mars, all 3 of those things that life needs were present. So does that mean life is ever there at the moment? Can't explain it. I can't confirm that. Is there life there now? Well, we can neither confirm nor deny. We can't go either way with it. So we need more study of that. Yeah.
Why was it warm enough to have liquid water if it did?
So what we think happened with Mars is that it did have a very thick atmosphere, just like the Earth did, or the Earth does still. And you need an atmosphere to both hold heat and also to generate the pressure to keep water in its liquid state. I can take water up to 50, 60,000 feet here on Earth, and then it'll start to boil off because the atmospheric pressure will be too low. So even at room temperature, it will boil into a gas. But on Mars, what happened is that Mars is smaller than the Earth, right? Have you guys ever cooked a potato before?
Yes.
Imagine you've got a really big potato, that's the Earth. You've got a small potato, that's Mars. You pull them out of the oven, which one's going to cool down faster? Small potato, yeah. So what we think happened is that the interior of Mars cooled down faster than the interior of the Earth did. So our magnetic field here on Earth is driven by that dynamo that we have at the core of the Earth. So all of that iron and stuff and nickel zipping around on the inside generating that magnetic field. And the solar wind is moved around by that magnetic field. So the solar wind doesn't really hit the Earth's atmosphere. So when Mars's dynamo died and its magnetic field died, the solar wind was able to go right at the atmosphere and start stripping the atmosphere away from Mars. And over hundreds of millions of years, it finally stripped away enough atmosphere that it made Mars colder and it lowered the air pressure, and then eventually that water either boiled off, evaporated, or froze. So finding water on Mars, you either find it as ice or as gas. So there is water on Mars. We found water ice there for sure. But liquid water, very hard to come by on the surface of Mars.
So did it take the oxygen?
No, there's still oxygen there. That oxygen bonded with carbon and it made carbon dioxide, and that's what Mars's atmosphere is. Mostly carbon dioxide and argon. So if you go to Mars, don't take your helmet off. So, yeah, not particularly good. But we also landed inside there as well, because like we were talking just now about figuring out the inside of Mars, we don't know what the inside of Mars is really actually like. We're just basing this off of our best scientific guesses. So InSight is there to measure all of that. So this is InSight just the day after it landed on Mars. And then this is InSight in April. And you can see we've already got a lot of dust on the solar panels, but it's okay. We've got plenty of power in order to power InSight. And InSight's mission is supposed to last about 2 years. We're already just over, just about 6 months into that mission. So we're doing pretty good so far with InSight. And it deployed a seismometer on the surface. The seismometer can measure movements down to half the width of a hydrogen atom.
Oh my goodness.
So, which is very, very sensitive. And we have to do that because it's one seismometer on the surface of Mars. As you probably, if you didn't know before, you probably know now after this past weekend that we have a network of seismometers here in California. So we're able to detect where earthquakes occur and do it very precisely because you can take those, figure out what the arrival times of the seismic waves are, and then pinpoint it exactly where those little circles around your seismometers are at, and that's where your earthquake happened. On Mars, because we only have one, we need to make sure that we can detect those seismic waves multiple times if they roll through. If we detect it multiple times, that tells us where the earthquake occurred at. So right about the third or fourth time those seismic waves roll through, we can figure out exactly where it occurred at. So that's why that seismometer is so sensitive with that. And it has a windshield that we put on top of it that protects it from the elements, so that way there's no noise or other things like that. But it is very, very sensitive. It's so sensitive that they need to know when the robotic arm of InSight is moving because the seismometer will detect it moving the air molecules around it.
Okay.
So, yeah, it's pretty intense. But from that, they've done some really cool stuff. Like they've actually taken those vibrations from the robotic arm moving and turned it into sound, so you could hear what it would sound like if you were standing next to InSight while its robotic arm was moving. We had another instrument on board called a heat flow probe. So basically, we hammer this probe into the surface of Mars. We measure the temperature and the fluctuation of the temperature in it over a very long period of time. And we figure out how much energy is leaving the center of Mars. But we have a problem, which is that we started hammering it into the ground and it immediately hit something and went askew. So we started pulling it back out, and just a couple days ago, they were able to pull that instrument all the way off of the surface and get what we call the mole, which is the part that hammers itself out in right there. So right now we're troubleshooting a geological instrument 180 million miles away from us on the surface of another planet. So we're trying to figure out how to get it back to work and actually make it work on the surface. But if anybody can do it, the folks at JPL are pretty good at doing stuff like that. So,
Well, figure it out.
yeah, they are working on it right now to figure out what to do with it. And I have not heard an idea yet as to what they're going to be doing with it, but they're working on it for sure. But we have our next rover on the way, which is the Mars 2020 rover, which you'll notice it looks a lot like which rover? It's a lot like Curiosity, right? Because it's a carbon copy of Curiosity. Yeah, we're using the flight spares for Curiosity to keep the cost down. But even though it's based on Curiosity, we're putting different instruments on it. We're doing all these other different systems on board. So we have the ability to not just take images like we do with our mass cam with Curiosity, but with mass cam Z, we actually got an optical element in it where we can zoom in and take really good photos of objects that are very far away from us. We have SuperCam up in the top of that mast right there, which SuperCam is a system that will allow us to look at a rock, fire a laser at that rock, analyze the gas coming off from where we're hitting it with the laser, and figure out precisely what that rock is made out of. So we don't actually have to go over to the rock anymore to figure out what it's made out of. We just shoot it with a laser. So yeah, pretty good stuff, right? That's pretty nice. There's also a RIMFAX in the back of it, which is going to be firing radar down into the ground, because we've only really been able to go a couple inches into the ground. So RIMFAX will go about 100 feet down and tell us what it looks like down there. Or is it mostly dust? Is there rocks and other things scattered about underneath the surface of Mars? So they'll be able to take a look at that. And also we've got Sherlock up on the end of the arm right there. Sherlock is actually going to allow us to figure out whether there might potentially be leftovers of biosignatures from life on Mars. So pretty exciting to have that. Because Curiosity, we sent Curiosity to figure out if there were places where life could have existed on the surface of Mars. And Curiosity basically found, yep, all over the place on Mars. So Sherlock is going to start looking for the leftovers of life on Mars. So if there ever was life on Mars, Sherlock will start to give us the evidence of that. And one of my favorite ones is Moxie, which is going to be on the inside of the rover there. MOXIE is a system that is going to pull in the atmosphere of Mars, the carbon dioxide atmosphere, and then see if we can actually pull that carbon out and make oxygen out of it. Because if you send astronauts to Mars, you need oxygen to breathe, right?
Yep.
So wouldn't it be nice if you could just like pull the atmosphere of Mars into a system and pull the carbon away from it and use the oxygen? Wouldn't that be nice? So also rocket fuel, you need oxygen for your oxidizer, right? So you could also help make rocket fuel with that as well. And when you pull your carbon away, you can end up making things like composites or carbon fibers by using it. So one of the ideas for human missions, especially human missions, is you don't actually take all of the stuff with you. You use the resources that are already there on Mars. So we were talking about mining Mars earlier. No need to bring your base with you. Just pull the iron oxide out of the surface and use metal 3D printing in order to build your base out of it. So MOXIE will be the first step in what we call in situ resource utilization. So basically, don't take all this stuff with you to Mars. Add more water, add more oxygen, add more science instruments, just build your base out of what's already on Mars. So, and hopefully too, that'll help us when we return to the moon as well, because I'm sure you probably know that we now have the new challenge of returning to the moon by 2024, but not just going there and walking around, like actually going and staying and being sustainable. So, in the back.
So the flags of the countries, are
Yes.
they participating? in
They are.
that?
Yeah, and some of them are participating, like Spain with their wind sensors. They're participating because their wind sensors got destroyed during the landing of Curiosity in 2012, just because of the way it worked. So they built new wind sensors that are a bit beefier, and they're going to be able to do that. It's just mighty nice to have 2 weather stations on different parts of Mars, so you can compare and contrast with that, and maybe start to build forecasts for the surface of Mars as well. So pretty cool stuff. But yeah, there is very rarely a mission where it is just purely NASA with the instruments on board. NASA is all about international collaboration. So anytime a partner would like to offer us an instrument, we're like, absolutely, yes, we'll take it. So, yeah, yes.
Notice you have thermal infrared sensors.
Uh-huh.
Is the temperature of the instruments on the satellite enough so you don't have to do an artificial cooling of it?
Yeah, and Mars helps us with that. So with as cold as Mars gets, it allows us to do that. Also with the new sensors as well, we can actually get them very, very cold without coolant as is. Yeah, so great question, yes.
Yeah, I'm looking at all this technology that's gonna be on this, rover. Does Mars have any seasons?
Oh, so does Mars have seasons? Yeah, yeah, sure does. It has winter, spring, summer, fall, absolutely. Yeah, it has 4 seasons just like the Earth does because of its tilt. So yeah, it's just its seasons are longer. So when we talk to kids, we say summer's twice as long, and they're like, yeah, 6 months of summer. And then we're like, yeah, but you get a year and a half of school. So yeah, so they really like that. But there's 2 very neat things I really like about Mars 2020, which is its landing system. So the landing system, we don't use airbags anymore because we're right at the limit of what you can land, period, on the surface of Mars. So we do have a heat shield. That heat shield has to handle the heat of entry, 5,000 degrees Fahrenheit, as we enter at about 13,000 miles per hour. But one of the things that's different from, say, InSight is that Mars 2020 will have thrusters on board of it, so that it will actually be able to do what we call guided entry. So as it's entering the atmosphere at hypersonic speeds, it will actually fly itself. It will figure out where am I located and then aim towards its landing site at Jezero Crater. Yeah, it's a very smart lander with this here. And there's a lot more smarts to it then. So it'll use those thrusters to also stabilize itself as well to give it the best possible opportunity for that. And then that parachute deploys at twice the speed of sound and slows it down very quickly. And then our heat shield pops off so the landing radar can figure out how high are we and what speed are we moving at. And then we are not going to just detach the Mars 2020 rover itself. We are going to have it attached to a rocket pack. And then that rocket pack will fire. We'll divert out of the way so that the back shell doesn't smack into it and then come down on its way. Now, our rocket pack on Curiosity just took it down to the surface and landed it. But this rocket pack will have cameras on board. And we will have the parts of Mars that it will be entering over preloaded onto the hard drives on board of the landing system. And the cameras will compare that to where it is at. And the cameras will go, the landing system will basically say, based on these images, I'm here. This is where big rocks are at. This is where interesting science is at. I'm now going to fly to the interesting science so the rover doesn't have to drive as far. And then when we get close enough to the ground, we don't want those rockets there because it will kick up dust and damage the rover. So we lower it onto these cables while it's still attached to the rocket pack. We deploy the suspension on the rover, and then once it gets to the surface, very, very carefully, it will indicate to the lander, I have reached the surface. We'll cut those cables, and then the descent stage will throttle up full and fly out until it's done with its fuel, and then just fall and crash kilometers away from the rover. And then we'll have Mars 2020 on the surface of Mars. So we call it the Sky Crane Landing System, and it looks absurd because it's crazy. So, but as we like to say, it's the right kind of crazy, and this system already worked for Curiosity. So we know that it will work for Mars 2020, or we're hoping it will work for Mars 2020. So, but another one of my, this was just from Curiosity. Curiosity had a camera on the bottom of it that actually took photos, about 1 photo or 3 photos per second on the way to the surface of Mars. So this is actually Curiosity's view of landing. So right now it's under a parachute coming into Gale Crater here. And we can see like these black sand dunes out in the middle that it had to traverse. And then eventually it'll become very, very smooth right here. And now we're under the rocket pack. And now we're coming up very close to the surface of Mars. And we're going to kick up some dust. We're good. We'll deploy our suspension. And then we'll drop down on the surface of Mars, just like that. So that was what it actually looked like with Curiosity. That's you riding along with it. But by far, my favorite thing that Mars 2020 is going to have is a helicopter demonstrator on board. So they have a little tiny vehicle that is going to have 2 rotors that are contra-rotating, so they both rotate in opposite directions of each other. And it's going to fly around in the atmosphere of Mars, and it's going to scout out areas that we want to drive Mars 2020. It's going to take photos. It may take videos. I'm not excited if it's going to or not, but it will fly out as far as half a mile from the rover, and then come back close to the rover and land, send its data, and then we'll use that to figure out where we're going to drive the rover. Now you may say, well, there's only 1% atmosphere on Mars if you have here on Earth. Well, they've already actually tested it up with JPL. They have a vacuum chamber up there. They pumped out all of the air to 1% of Earth. There it is. It flies perfectly fine. So, yeah, pretty amazing if they're able to get that.
Why just the radius of half a mile?
Oh, we don't want it to fly too far. So we want to put a transmitter in it, and we don't want that transmitter to be too big or require too much power. So half a mile is about what they're going to limit it to, and then they'll fly it on back to land near the rover. Not on the rover. We don't want it to like crash into the rover. That's bad. But yeah, that will most certainly be entertaining to see. And I love the selfies that Curiosity takes already, because it has a camera at the end of its arm. So it will take these amazing selfies of itself. I now cannot wait for the helicopter to take like a beautiful landscape photo of Mars with a rover sitting there, and knowing that is a real image that we have taken. So Mars is an incredibly complex place, even now it's an ancient place. We know in Mars' past that it really did probably look just like this, like the Mojave Desert, but right next to an ocean. So our continued exploration of Mars, we're trying to figure out everything we can about Mars, and maybe see if that life had been there, or, eventually us as life will return to Mars. So thank you guys for listening in. I appreciate you inviting me out here today. And if you have any questions, you can ask them. You can also come on up and ask them as well. I don't want to hold you any longer than you guys have today, but thank you so much for listening in today. And if you'd like to, you can head on over to jpl.nasa.gov, and you can check out some of the cool things that JPL is doing. You can watch that live feed of them building the Mars 2020 rover. And if you go there as well, make sure to sign up for your ticket to Mars, because if you, no, really, if you go on JPL's website, you can actually go to a place where you can put in your name, and they will actually be etching your name onto a microchip that will be attached to the Mars 2020 rover. And you can get your own boarding pass for that as well. Print it out, basically show everybody, yeah, I'm going to Mars in 2020, so no big deal. So once again, thank you folks for inviting me out here today, and if you have any questions, feel free to come on up and ask them. Thank you so much.